Hi, welcome to Mrs. Ballard's class. Today we're going to be talking about calculus topic 1.14, where we are connecting infinite limits and vertical asymptotes. So today's lesson objectives are the essential questions are how do you determine the behavior of a function whose limits involve infinity, and how do you find a vertical asymptote? And as a reminder, you should be answering those questions in your summary of the lesson each day. We've got two I can statements as well. I can determine the behavior of a function using limits that involve infinity, and I can find the vertical asymptote. Now, as always, feel free to pause if you need more time to write those down, or at any time during the video. And remember, you can always rewind or back it up if there's something that you didn't catch. Okay, so here we go. Let me flip my computer around here. Hey, and we're going to look at those asymptotes with the elephant here today. Okay, so as always, we're going to write our name on our paper. So we make sure I know who it is when you go to turn these in. Okay, as they will not be accepted without your name up there. So we're going to consider the following limits in their graphs. So they gave us not only the function, but they also gave us the graph of the function. It looks like we've got some asymptotes there. We're going to find the limit of each and confirm the result with the graph above. So I'm going to use my graph actually to find them. So as the limit as x is approaching 1 from the left, so as I'm coming at 1 from the left side of the graph, I notice I'm going down, 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 down. The y value keeps going down, so it means it's going to negative infinity. I need to approach 1 from the right, so there's 1. I'm going to come out at my graph from the right side. I'm going up, 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 up. That means I'm going up to positive infinity. You don't have to write the positive, but you can. And then it's asking for the limit of 1 overall. And because our right hand and our left hand limits do not match, we know that our limit does not exist. And if you wanted to write a reason, right and left limit not equal. Good to know for yourself, just so when you're going back and reading your notes, you understand that. So the limit as x approaches 1 from the left side, so I'm going to do that. Looks like I'm going up, 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 up to positive infinity. And then as we're coming at it from the right side, I go up, 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 up to positive infinity again. And what do you know? They match. We know that we have an infinite limit. It really doesn't exist. So because it increases or decreases without bound. And that's a reason for a limit to not exist. We had learned in an earlier lesson. So this one actually is also D and E. And I would definitely write that down because that way you remember why it does not exist. So you got a little think about it question here. You might want to pause and read it and then kind of write your own thoughts on it and then come back and see how I answered it. So what do limits that produce results of infinity or negative infinity say about the function? Well, if I'm getting limits of infinity or negative infinity, every time I do that, you'll notice I have this thing in here that we call the vertical asymptote. So if I have an infinite or negative infinite limit, I know that I'm going to have an asymptote. So at that location. So I'd say they represent locations of vertical asymptotes. That's an M. All right, and then the official definition of a vertical asymptote. So if the limit as x approaches c of f of x, c from the left, sorry, of f of x equals, that's an equal sign, infinity or negative infinity, or the limit as x approaches c from the right of f of x equals infinity or negative infinity, then x equals c is a vertical asymptote. So we saw this graphically. Now we're going to go ahead and find those vertical asymptotes analytically. And remember, this is actually kind of an algebra 2-ish skill. that we should have covered in there. So when we're looking for vertical asymptotes, we really don't have to do any limit notation. This really isn't calculus other than we know that they're there because of their limits. It's the official definition, but really what you're going to do is you're going to factor and cancel, and then anything left in the denominator is a vertical asymptote. So anything left in denominator is your vertical asymptote. All right, so let's check it out. So I'm going to go, I can't factor the numerator because that's a sum of squares, but I can definitely factor the denominator. That doesn't really help me though, does it? X plus 2, x minus 2. So that didn't help me a whole lot, but that's okay. I'm just going to go ahead. So these are the two things that are remaining in the denominator, so I'm going to set them both equal to 0, and that will give me my vertical asymptotes. So I've got a vertical asymptote at x equals 2 and x equals negative 2 and x equals 2. This one here definitely factors a little bit more than the last one did. So let's see, magic x, because it's a trinomial. So two numbers that multiply to negative 8 and add to 2 would be 4 and 2. Looks like 2 needs to be negative. So my numerator is x plus 4 times x minus 2. The denominator's difference of squares, so x plus 2, x minus 2. And now we know we're going to cancel. We cancel, remember cancel equals a whole, or implies a whole. So this one would have a whole at x equals 2. Okay, we didn't need to have that. That's not what we were looking for, but that's what's going on. What's left behind, this guy's left behind, that's our vertical asymptote. So x plus 2 equals 0. So our vertical asymptote is at x equals negative 2 on that one. So just a handy little tip. It's likely that by now you've discovered that for fairly simple rational functions, finding the location of any vertical asymptote can be done without actually finding the value of c that x should approach to ensure a limit that approaches either positive infinity or negative infinity. It is possible to find the asymptotes by reducing the rational function to its simplest form and then setting any denominator factors equal to 0. That's basically what we wrote down up here, isn't it? Okay. So we're going to determine any more. So this is kind of more of the same, but there's a little bit less to do actually. There's nothing to factor in a, so all I'm going to do is just set what's left in the denominator that has a variable in it equal to 0. The 2 we can just ignore. So x plus 1 equals 0. So my vertical asymptote is that x equals negative 1. This one here, I don't have a denominator, but I know that I could get a denominator by using a trig identity. I know cotangent is the cosine of x over the sine of x. So this is going to have vertical asymptotes anywhere where the sine of x is equal to 0. Okay, so that means that the y value, or the y value has to equal 0. So that means I want anywhere where the y value coordinate, I need the radian measure to figure out the radian measure. I know my radian measure here is 0 and my radian measure here is pi. So I know that this happens at 0 and pi, but don't forget that this cycles around, doesn't it? So doesn't it also happen at 2 pi? And then at 3 pi? And then again at 4 pi? And couldn't I go backwards? I could go backwards to negative pi, or negative 2 pi, or negative 3 pi, and so on. This one didn't put a domain or restriction on it. So there's lots of vertical asymptotes. You could, typically in calculus, we usually stay between 0 and 2 pi, so we would have really only had these 3 answers, but it just depends on how the question is asked. All right, and our final question here, we're supposed to be trying to figure this out without using our calculator. So let me see if I can work you through the fractions a little bit. So try to find the limit of each without using a calculator, and try making a table of values to allow you to get closer to 1 and approximate the side of 1. So if I was going to think about something that's close to 1 on the left side that's just less than it, I'd think 0.9. And then maybe I'd think 0.99, and then maybe 0.999. So if I start putting that into here, I'm going to do some scratch work over here. 0.9 minus 1, well, that leaves me with 0.1 left. 0.1 is 1/10, and then if I flip and multiply that, I get 10 over 1, or just 10. All right, let's try that same pattern here. 0.99 minus 1 would be left me with 0.01, which that's 1/100th. So when I flip and multiply that, I get 100. Guess what's coming next? So 0.999 minus 1 would be 0.001, which is 1/1000th, which if I flip that and multiply, I'd get that it was 1,000. And you can see how that number, no matter, I'm getting closer and closer and closer to 1, but that number is getting really, really, really big, which means that this limit is going to negative, or sorry, this one's going to positive infinity on that side there. Minus 1. Yeah. Did I do something wrong? I think I did. Shh, I did. All right, so look at this. It should have been negative 0.1, which makes it negative 10, right? And this one should have been negative 0.01. I missed my sign up. And this one should have been negative as well. So we just got to swap our signs. So it's actually going to negative infinity. All right, let's do the same concept over here on this one. So this time, just on the other side of 1, I would think would be 1.1, and then maybe 1.01 and 1.001. So if I do 1 over 1.1 minus 1, I'm going to be left with 1 over 0.1, which is 1 over 1/10. Hopefully you're getting the idea here. 1/10, which again, if I flip and multiply, is going to be 10. All right, I'm going to do 1 over 1.01 minus 1, which is going to be 0.01, which is going to be 1 over 100th. And then I'm going to multiply by the reciprocal, so I get 100. And guess what? This one is 1,000. So again, this is getting really, really, really close to 1, but this is getting really, really, really gigantic. So this goes to infinity. And we know that that means that there is no limit. The limit doesn't exist overall in this one, because actually it goes to infinity in both cases. So we would say that the limit as x approaches 1 of 1 over x minus 1 does not exist. And that's it for today's lesson.